This is a really fun lab on thin lenses. A lens is a optical device that looks like this. This is called a convex lens. Uh, it's a spherical lens because you can imagine that it's part of a much bigger sphere. So see, there's a sphere right here, a spherical surface, and then this other surface. So you have these two spherical surfaces right here. We use a couple of things to define them. First is the center of curvature, I'll call that C, and then there's a center of curvature over here. That's actually the radius of the sphere from which it was cut. And then there's also the focal point, and the focal point is here. These are the focal points. The focal point is equal to 1/2 of the center of curvature. The focal point is also where parallel light rays are focused. So, well, for example, if we have a lens and have some object that's really far away, and when an object is really far away, the rays from it coming from that object are going to be parallel. It's sort of like how we're really far distance from the sun, and by the time the light rays get to us, even though at the surface of the sun they're divergent, by the time those rays get to us, we're just sampling such a small portion of the sun's light that those rays are parallel. Anyway, these light rays are going to focus at the focal point. So that's another way to get the definition of the focal point. And then, of course, this is a biconvex lens, so it has two focal points. So that's how we define the focal point for a lens. We can also talk about the image and the object distance. So if I have a lens right here, the image distance, my focal points here and here, the image distance is the distance from the lens to where the object is located. So this is P. Now, in your lab manual, it talks about how this P is equal to the lens position minus the object position. Because on your optical benches, you'll have positions. There's a ruler on your optical bench, and you can read the position of the lens and the position of the object. But nonetheless, it's just referring to the distance between the lens and the object. Then wherever the image is, the distance from the lens to the image will be the image distance. Now, how can we figure out where the image is going to be? Let me give you a brief explanation of how to draw rays for these lenses. I'm just going to give you two of the rays that you can draw, but in the lab or in the course, you'll learn how to draw other rays as well. The first one is if I have an incoming ray that's parallel to the axis, the optical axis, that's the axis that runs along there. If I have a ray that's parallel to the axis, it will go through the focal point. Right, that's how we define the focal point. So if I have a ray that goes parallel to the axis, it will go through the focal point. And then the other way is just the opposite of this, is if I have a ray that goes through the focal point, it will be parallel to the axis. So that other ray, see here's my focal point right here, it'll go through the focal point, and then it goes parallel to the axis. Now, the image for this object is going to be right here where those two light rays cross, and since they cross at a point below the optical axis, that image is going to be inverted or upside down. The distance to this image is called our image distance, that's Q. It's image distance. And in your lab manual, it talks about how this is the difference between the image position and the lens position. We can define the magnification in a couple of different ways. I'll put it here, magnification. The magnification is equal to the height of the image divided by the height of the object. In your class, we call this height HI over HO. That's the height of the image divided by the height of the object. The height of the image is just right here, or this is Y prime. The height of the object is just this, or we call this Y. That's the height of the image divided by the height of the object. You'll see for here, this HI is a negative value, so your convex lens, when you have an object outside of the focal point, has a negative magnification. So here, this image has a negative magnification because Y prime is also negative. So that gives you a negative magnification. Another way to calculate the magnification is to say that the magnification is equal to the negative of Q divided by P, where Q is our image distance and P is our object distance. So again, let me just say this regarding magnification. If magnification is negative, that means that the image is inverted. Mathematically, that works out because your y prime value, or your height of your image, has a negative value. If it's positive, that means that you have an upright image, because both y and y prime are positive, so your magnification is positive. We'll talk more about those types of images in the course. And if m is bigger than 1, that means the image is bigger than the object. And if m is less than 1, that means the image is smaller than the object. Those are important ideas to remember in this course, in the lab, and then also in the lecture component of the course. Let's look at a two-lens system with a virtual object. So here we're going to have two lenses, two thin lenses, two convex lenses, and they're going to be positioned in such a way. Well, let's just draw this one first. So let's say that there's my first lens, and my object is out here somewhere. And then if I draw the rays for this, I will find that the image is right here. I have an image right there for the first lens. Then I'm going to take my second lens. I'll do it in black. So we call this our object lens. The test lens, which you're going to place in here, is going to go right about here. Right, it's going to go pretty close to the first lens. And it's going to create an image that is going to be right about here. So this is our virtual object right here. And this is our final image. What's happening here is that the image from the first lens, that's our object lens, that's the first lens that we put in, becomes the object for the second lens. That's our test lens. That's what we're calling our test lens. When that happens, we can use our lens equation. Our lens equation describes the relationship between the focal length, the object distance, and the image distance. And we can use this if we know P and we know Q, then we can solve for F. And so we're going to do that here, or if we know F and we know the object distance P, then we can solve for where our image is. We're going to use this here to figure out what is the focal length of our test lens. So we're going to measure P for the test lens, measure Q for the test lens, and then we will we'll figure out what is the focal length. Now, P for this test lens is the distance from here to here. So remember, this was your image from your first lens. We find out where that is and we note the position of it. And there's a place in your lab manual to note the position of the image from the first lens. But this becomes the object for the second lens. Then we find the second image, and this becomes the image distance for the second lens. So now we have P2 and Q2, so we can solve for F2. something funky happens here because we have what's called a virtual object. We call it here. This is a virtual object. What that means is that the object is on the side that's opposite the side from where the rays are originating. The rays are coming in from this side. They're traveling in this side, going from left to right. But notice that the object is on the right-hand side. So it's called a virtual object. And when you have a virtual object, the object distance is negative. So whatever we find P to be, that distance, that's going to be, we're going to give that a negative value when we're doing our calculations. Okay, one other thing about lenses is that they experience something called spherical aberration. And spherical aberration occurs when you have light rays that come in at one point of the lens and they focus at a particular point. And then you have light rays that come in on another point of the lens and they focus at another point. Spherical aberration happens in all spherical optical devices. So if you have a mirror, for example, and you have light rays that come in, they focus at one point, and then you have light rays that come in at another point on this mirror, and they focus at another point. You can get rid of spherical aberrations in a number of different ways. One thing that we do in telescopes, not uncommonly, like fairly frequently, is instead of having a spherical mirror, you'll have a parabolic mirror. And I'm exaggerating it here, the parabolic shape. But when you have a parabolic mirror, light rays will focus at the same point. Another thing that you can do is you can put in other lenses before the device, and that causes the light rays to bend in a particular way so that you get rid of the spherical aberration. We're not going to do that. The human eye, which I think is a remarkable optical device, uses an aperture, and that's what we're going to do today. We're going to take an aperture and block out the light on the outer parts of the lens, and that causes this part of the image to go away. You see, when you get these two different focal points, that creates images at two different points in space, which creates a fuzzy image. Right? That is a fuzzy image, that you have an image at one focal point, and then you have another image at another focal point, and it makes for a fuzzy image. So we're going to use an aperture to measure, or to figure out, to get rid of the spherical aberrations, and then we're also going to use that aperture to figure out what are the two focal points. So we'll call this F2, and then we'll call this F1. To determine the spherical aberration, we take the difference in these two focal points. So that's going to be F1 minus F2. I'll show you how to do that with the optical bench, but in short, you're going to measure the focal point using these different apertures.